In this example, we know that the coefficient performance of a freezer is 2.25. The freezer is able to take 2 kilograms of water at 20 degrees Celsius to ice at minus 5 degrees Celsius within 45 minutes. We want to know how much energy must be removed from the system to make that transformation, how much work must the freezer do to remove that energy from the system, and how much waste heat must be expelled to the environment. Alright, so first we want to calculate how much energy must be removed from the ice, or from the water, in order to turn it into ice. That means we need to calculate 3 Q values. One to take the water from 22 degrees down to the melting point of 0. One to actually melt the ice, and then one to take that ice from 0 degrees down to minus 5 degrees. So I have looked up the specific heat of ice, the latent heat of fusion for water, and then the specific heat of water. And I calculated a Q value of negative 8.7 times 10 to the 5 joules. Remember, all of these are going to be negative. The temperature changing ones are going to be negative due to delta T, but you have to remember to put the minus sign in front of the mass times the latent heat of fusion. In part B, I want to know how much work has to be done in order to remove this energy from the system. So I know the coefficient of performance is equal to QC divided by the work. And the QC value is how much energy is coming from the refrigerator into the coolant, which is going to be the amount that we calculated in part A. And we know the coefficient of performance, so we can calculate the work. And then we want to know how much energy must be expelled through heat to the environment. And that's going to be the sum of what was removed from the ice, or from the water to turn it into ice, and then from the work that had to be performed on the coolant in order to get it to the appropriate temperature in order to remove it, or remove that energy. So I've added together the two energy values I found and got a total of 1.26 times 10 to the 6 joules.